right, so if we're going to talk about continuity, we kind of have to know the opposite of continuity. Okay, so we got to talk about discontinuity first. And so could you give me some types of discontinuity before we talk about the actual continuity thing? Okay, all right, I heard infinite. When will infinite discontinuities occur? Okay, so those are going to be, or you can call them asymptotic. Oh yeah, right. I meant to write that. All right, so we got infinite. Give me some other types of discontinuity. Jump. Okay, sometimes jump, which we just saw, that integer function is a classic jump. Sometimes they call that gap as well, gap discontinuity. More? Removable. Okay. Removable is just a pinprick. It's just that one little pixel removed due to division. Okay, and then there's the one that's not super common. Yeah, it was the word we spelled earlier. Oscillating. Okay. Okay, so those are some of the types of discontinuity. If you want to write that example, so if you're ever thinking of, what was that again? It's sine of 1 over x. All right, so then we need the proof for continuity. All right, so the proof for continuity is threefold. F of A must exist. Okay, so the point has to be there. It has to be. That means it has to be closed. The limit approaching A from the left must equal the limit approaching A from the right. That's the third part. So you got 1, F of A must exist. 2, the left and right hand limits must exist. And 3, what must be the final conclusion? All of that should equal the same number. Because you could have F of A exist and be something, and you could have the two limits exist and be equal, but you don't necessarily know if all three of those things are equal to each other. So that's the last part that makes something continuous, is that F of A must equal the limit as x approaches A that you just established from the second part of it. That's the proof for continuity. You have to state that final thing, that those things are all equal. Because an example, a counter, let's see. All right, a counter example might be like this. Okay, so there's a counter example. F of A exists. I see the point. Here it is, F of A. I also see that the limits on both left and right hand sides, okay, there's the limit, they both equal, and so we have the limit as x approaches A of f of x, that exists. The problem is those two things don't exist with each other and aren't equal to each other, so that would be an example of a discontinuity. You've got to be able to prove all three things are all the same. All right, so let's talk about Justine's step function that she discovered today. In symbology, the step function is written like that, using brackets. And equivalent is to write intx. They both are the same thing. Okay. All right, if I asked you, okay, is that continuous? Prove it. Okay, prove it. So give me a specific, like pick an A and prove it. You want to pick 0. All right, so let's prove it. What is f of 0? 0. Okay, well that exists, so that's fine. Okay, what is the limit as x approaches 0 from the left and right? Okay, well what's the limit approaching 0 from the left? -1. Limit approaching from the right? 0. So I got 2 out of 3, but so there's your proof. Okay, it only takes one case, one example, to prove something is discontinuous. Okay, it only takes one. You can pick whatever A you want to prove that it's discontinuous. To prove that it's continuous, it has to be true for every value of A. To prove discontinuity, you only need the one case. All right, so let's look at a trig function. Okay, g of x equals cotangent. Okay, we know it's discontinuous. It's got a whole bunch of vertical asymptotes. Okay, prove it. Pick me a position and prove that it's discontinuous. Catherine, what do you want to do? Okay, so f of 0. Okay, what's f of 0? All right, so I'm going to pause this a sec. All right, f of 0. Case closed. Okay, like we're done. It doesn't even, we don't even have to worry about it. It only takes one counterexample. Now, could you fake it? And okay, what if someone picked pi over 2? All right, well, what is the function? Oops, I should be doing g. Sorry, I decided it was going to be g. Yeah, I don't know if I can still erase that. Nope. Okay, so what is g of pi over 2? 0, right, for cotangent. And then what is the limit as x approaches 0 from the left? Oops, x approaches pi over 2 from the left, and the limit as x approaches pi over 2 from the right of the cotangent of x. Okay, that's also 0. Boom, cotangent is continuous. I mean, you could try and fake it, right, and try and, all right, but it has to hold for every value of A. So it's a lot easier to prove something is discontinuous. You just got to find one. Yeah.
What if it's like if it's a function where we don't automatically know that it's discontinuous and we don't know where the discontinuity is? How do we find out where it is?
Okay.
So
right.
You could just, if we didn't know that it was discontinuous at 0, then
you know a lot more than you're giving yourself credit for. Okay, a function can't be discontinuous unless really it has a denominator that would be equal to 0, right? Or if it was like a piecewise function that had a jump or a gap in it. I mean, you know a lot more than you think. What about a function like natural log? Okay, now natural log only exists on which half of the graph? Okay, the positive half, assuming that we're just doing regular natural log. Is that continuous? Okay, and the answer is yes, because you don't have to consider its domain, the part of the domain that doesn't exist. And so you would only be able to prove discontinuity of natural log if you could prove the failure of the 3 conditions. And with natural log, you can't prove the failure of it, and so then the conclusion is that it is continuous on its domain, which is everything to the right of 0. Okay, so you know, The discontinuities like infinite are easy to find because they deal with the denominator. Jumps and gaps are piecewise functions, so by definition you should be able to spot those pretty quick. Removable, that's going to come where you have to factor. Okay, the oscillating ones are the tougher ones, and you'll usually have your graphing calculator to check the shape of that one, because those are harder to spot because they don't have anything identifiable. I mean, I guess the only thing I would say, well, the function sine of 1 over x, you know there's got to be a problem at 0 because of the denominator. Those are the only four. Those are the only 4 categories. Oh, yeah.
They all kind of look the same, where they just kind of spaz out at one point.
Right, but you maybe wouldn't see it, like, it wasn't super obvious to me when we looked at it until we zoomed in a little bit.